Ever wondered how a neural network works? Imagine a computational model inspired by the structure and functioning of the human brain. This is the essence of a neural network. It's a fundamental component of deep learning, a subset of machine learning. But what exactly is it and how does it operate? Picture a system of interconnected nodes, also known as neurons or artificial neurons, organized into layers. These layers include an input layer, one or more hidden layers, and an output layer. Each connection between nodes carries an associated weight. Each node applies an activation function to its input. Sounds complex? Let's break it down. The neural network begins its journey at the input layer. This layer consists of nodes that represent the features of the input data. Each node corresponds to a specific feature or attribute. The values of these nodes form the input to the neural network. Next, we move on to weights and connections. Each connection between nodes carries an associated weight. These weights represent the strength of the connections. During training, the neural network learns optimal weights that enable it to make accurate predictions. Between the input and output layers, we encounter one or more hidden layers. These layers empower the neural network to learn complex patterns and representations from the input data. The nodes in the hidden layers apply activation functions to weighted inputs, generating output values. What are activation functions, you might wonder? Each node in the network applies an activation function to its input. This function introduces non-linearity to the model, allowing it to learn and represent complex relationships in the data. Common activation functions include sigmoid, hyperbolic tangent, and rectified linear unit. For each node in a hidden layer or the output layer, the weighted inputs are summed, and the result is passed through the activation function. This process repeats for each node in the layer. Finally, we reach the output layer. This is where the neural network produces the final results or predictions. The number of nodes in the output layer depends on the nature of the task. For binary classification, there might be one node representing the probability of belonging to a certain class. In multi-class classification, there will be multiple nodes, each representing a different class. Once predictions are made, it's time for the loss function. The output of the neural network is compared to the actual target values using this function. The loss function quantifies the difference between the predicted values and the actual values. The goal during training? Minimize this loss. Now, we come to backpropagation and optimization. Backpropagation is a process used to update the weights in the network to minimize the loss. It involves calculating the gradients of the loss with respect to the weights and adjusting the weights accordingly. Optimization algorithms, such as stochastic gradient descent, are commonly used to update the weights iteratively. Training involves feeding input data, making predictions, calculating the loss, and updating the weights. This process is repeated iteratively over multiple epochs until the model converges and achieves satisfactory performance. Once the neural network is trained, it's ready for inference. It can be used on new unseen data. The input data is fed into the trained network, and the model produces predictions based on its learned weights and representations. The power of neural networks lies in their ability to learn complex relationships in data. They are used in a wide range of applications, from image and speech recognition to natural language processing. So, next time you wonder about the magic behind these technologies, remember the intricate workings of the neural network.